What's the real difference between an AI model that changes the world and one that, well, can't even get the basics right? It's not always about having more data or a bigger computer. A lot of the time, it comes down to a handful of settings, these secret controls that can unlock a model's genius or doom it to failure.
So what are these secret settings? What are these hidden dials and knobs that engineers are turning to get these incredible results?
Well, they have a name. They're called hyperparameters. And instead of just giving you a dry textbook definition, we're going to decode them together by actually walking through how you'd build a neural network step by step. Let's dive in.
So, here's our roadmap. We'll start with what these things even are. Then, we'll get our hands dirty designing the network's blueprint, we'll set up its learning engine, and finally, we'll actually run the training process. By the end, you'll see exactly how all these pieces click together.
Okay, first things first. What exactly are hyperparameters? The easiest way to think about them is as the high-level dials and knobs you get to turn on your AI model.
So here's the more official definition. They're the settings that you, the builder, use to define the network's structure and control how it learns. And here's the most important part. You have to decide on them before you start training. They are the rules of the game you set up front, not the moves the model makes while it's playing.
All right, let's move on to our first big step, building the network's architecture. I'd like to think of this as creating the actual blueprint for our model.
Every network has to start somewhere and end somewhere, right? It's got an input layer and an output layer. Now, the size of these isn't really a creative choice. It's dictated by your project. Your input layer has to match your data's features. Got 10 features, you need 10 input neurons. Simple. And the output layer has to match your goal. Trying to classify images into 4 categories, you're going to need 4 output neurons. And if you're using a framework like Keras, this is super straightforward. If you have a 28 by 28 pixel image, you just flatten that into 784 inputs. And for that 4-category problem we just talked about, you'd make a dense output layer with exactly 4 neurons. Done.
But the real magic, the part where you get to be an architect, happens in the middle, in what we call the hidden layers. This is your domain. You decide how many layers to stack up and how many neurons go in each one. This is how you control the model's capacity to learn. And here's a little pro tip. If your model isn't learning well, try making it deeper by adding more layers before you make it wider by adding more neurons. Deeper is often better.
Now, for any of these layers to do anything useful, each little neuron needs an activation function. Think of it like a tiny on-off switch. It decides if that neuron has seen something important enough to fire and pass the information to the next layer. This is absolutely critical because it's what lets the network learn complex, twisty, turny patterns in the data.
And I really can't overstate this. If you don't use a nonlinear activation function, your fancy deep neural network, no matter how many layers it has, is basically just a simple linear equation. It can't learn anything complex. It would be like building a race car that can only drive in a perfectly straight line.
So you've got to pick the right tool for the right job. For hidden layers, a function called ReLU is the go-to choice for almost everyone. Simple, it's fast, and it works really well. Then for an output layer that's doing multi-class classification, you'd use something called softmax, which is perfect because it takes the model's raw scores and squishes them into nice, clean probabilities for each class.
Okay, 2 final architectural choices to touch on. First is weight initialization. This is all about how you set the initial connection strengths. The key rule? Never, ever start them all at 0. If you do, the network just won't learn. The other is regularization. This is a set of techniques, like dropout, that you use to stop your model from cheating by just memorizing the training data. It forces the model to learn real, general patterns.
Phew. Okay, the blueprint is designed. Now it's time to tune the learning process itself. This is kind of like choosing and configuring the engine that's going to power our model. At the heart of that engine is the optimizer. This is the algorithm that actually does the learning. It's what updates all the network's weights to make it smarter. The classic is called stochastic gradient descent, or SGD. But honestly, these days, optimizers like Atom are usually a fantastic starting point because they're more adaptive and can often find a good solution faster.
But how does the optimizer know which direction is smarter? That's where the loss function comes in. You can think of it as a scorekeeper. It calculates a score based on how wrong the model's predictions are. The optimizer's entire job is to tweak the weights to get that wrongness score as low as possible. And just like with the output layer, you have to pick the right scoring system for the game you're playing.
So in Keras, you wire up the optimizer and the loss function together in one line of code during the compile step. And this is also where you set one of the most famous and most important hyperparameters of all, the learning rate. This little number tells the optimizer how big of a step to take with each update. If it's too big, you'll just bounce around and never find the answer. Too small, and training will take forever.
All right, our engine is built and tuned. Now it's time to fire it up and actually start learning. This brings us to the final set of controls, the ones for executing the training loop.
Okay, let's quickly clear up two terms you will hear all the time: batches and epochs. It's actually pretty simple. Instead of showing the model all the data at once, we break the data set into smaller chunks, or mini batches. The model looks at one batch, makes an update to its weights, then looks at the next batch, makes another update, and so on. Once it's gone through every single batch and seen the whole data set one time, that's one epoch.
So what's a good batch size? Well, you'll see powers of 2, like 32, 64, or 128, pop up everywhere. And that's not an accident. It's because modern computer hardware, especially GPUs, is designed to work most efficiently with data in these nice, neat binary chunks.
And putting this into code is the easiest part of all. When you're finally ready to kick off the training, you just call the fit function. And that's where you tell it your batch size and the total number of epochs, or full passes through the data, you want it to run for.
And that's it. We've looked at all the individual pieces, the layers, the optimizers, the batches. Let's take a step back and see how this whole hyperparameter jigsaw puzzle fits together.
Here's the way I think you should approach this. Some of these settings, like your input and output layers, are basically decided for you by your data and your goal. Some are guided by well-established best practices, like using ReLU in your hidden layers. Then you realize some of them are connected. Your choice of activation can influence your choice of weight initialization. And finally, some of it is just art. It requires experimentation, intuition, and a bit of trial and error. It's this fantastic blend of science, engineering, and creative tuning. But these are the fundamental controls, the knobs and dials you need to master. So now that you know how they work, what are you going to build first?